Hello, we are Team 3M, and today we would like to introduce our semester-long project on an autonomous vehicle and drone integrated system for disaster prevention. Among them, we will focus on the self-driving part. First of all, the overall flowchart of our team. As you can see, the local dynamic map team created HD maps, and then the teledriving team and the driving DAQ team aim to simulate and remotely drive based on the maps. We also studied precise positioning technology through cameras for disaster prevention in urban areas. Let's start with the LiDAR SLAM part of local dynamic map team. We developed an algorithm to extract the ground at the same time as driving and autonomically extract lanes based on intensity. And we also created HD maps for transverse and longitudinal traffic lights. Confirm the accuracy of the map with future points. Transverse traffic light markers from an HD map were matched with their 3D counterparts. The left image shows the alignment of a red ground truth marker with a red point cloud traffic light, while the right image demonstrates lanes recorded alongside data acquisition. Created a prototype map using the point clouds and labeled landmarks that were detected and stored in real time. Next is the visual SLAM part. This is the framework of our pipeline. This is a part of the process for creating an Orbi SLAM 3 map on the rectangular site in Songdo. We conducted SLAM over several laps to enhance the accuracy of loop closing. Then we stored and processed the VSLAM results as a point cloud map and compared them with the LiDAR SLAM results. We expected problems in rotation translation scaling because VSLAM uses a different coordinate system in origin and is not expressed in meter. To solve the rotation and translation problem, we used camera LiDAR calibration results, and for the scale, we calculated the distance ratio between the actual traffic lights and the distance between the traffic light features. The left image is a result of our previous hand-on calculated method. You can see that it doesn't fit well. The right image shows a result based on LiDAR camera extrinsic calibration results. You can see that it is more accurate. This confirmed the accuracy of both the extrinsic calibration and VSLAM. Local dynamic maps visual localization involves two main steps, mapping and localization. In the mapping process, points within 20 meters are projected onto an image plane aligned with the ENU coordinate system. Each projected point's feature descriptor is extracted and saved along with its 3D coordinates. This prepares the system for visual localization, where the camera pose is estimated in relation to this map scene. Following is the visual localization process. Extract the feature descriptor from the real-time incoming video, match the stored feature descriptors to create 3D 2D point pairs, and estimate the camera pose using the solve PMP algorithm with the 3D 2D point pairs. Following is a comparison of the position estimation results with the ground truth values obtained from the GPS sensor. Next, we will present the driving DAQ team. We chose AutoWare because it's open source and a platform that not only collects autonomous driving data, but also manages the overall autonomous driving process. AutoWare's structure is composed of three main stages: sensing, planning, and control. Sensing involves collecting data via LiDAR, GPS, and cameras for obstacle detection, positioning, and recognition of road elements. In planning, the data leads to strategic decisions for navigation. Control executes these decisions to steer the vehicle. This system allows autonomous vehicles to smartly navigate and adapt to road conditions. AutoWare supports a wide range of sensors, making it versatile for use with various hardware. If you wish to enable autonomous driving on your vehicle in a specific map using AutoWare, you only need to modify four key files: launch file, vehicle launch file, sensor launch file, and map data. This video is autonomous driving in AWSIM by AutoWare. Simply by setting the destination, the system automatically performs global path planning and, upon perceiving objects in the surrounding, initiates local path planning as well. It is important to note that AWSIM only provides sensor data, time values, and vehicle state information, with all perception, planning, and control processes carried out through AutoWare. Lastly, we will present about the teledriving part. Teledriving is a technology that enables remote control through communication between a remote operation center and a vehicle. Commands are issued from the control center to the vehicle, and the vehicle sends driving data back to the control center. Teledriving is a solution for emergency situations during autonomous driving. There are three essential elements for tele-operated driving system. Firstly, the vehicle with hardwares like camera and softwares like control systems. Secondly, stable and low latency network. Lastly, the operator. Screens, computation units, control devices are needed. The problem of this system is the latency. From the vehicle cameras to the operator's display, there are many sequences to process the information. How short and how stable this latency is most important for the system and the safety. This is a demo video of what we experienced. Because of the lack of inertia, it was difficult for the system to adapt. However, the latency was quite stable, so we thought that the teledriving system could deal with the failures of autonomous driving. We plan to further refine our system based on these findings. Lastly, thank you for listening to our presentation.